To start with optimization. So essentially numerical optimization, something that should not be completely novel to everyone, because we already discussed optimization in the winter term for, I think, a couple of things. So we had maximum likelihood estimation, and then I discussed how to analytically determine the maximum of the likelihood function for the GLM. And I think we also discussed, when we discussed restricted maximum likelihood estimation, that there are things like Newton algorithms are being used. As this Fisher scoring method, and similar stuff we also discussed in statistics for data science. So it's not completely novel to everyone that optimization plays a role. But I thought rather than bringing it up on occasion, so basically when we get to a certain point when discussing a machine learning method, and then bring up some principles of optimization, I decided to put it out there up front, because it's very important, and it's usually where things become a bit complex, if you want. So usually understanding a certain machine learning model is relatively straightforward. So for example, neural networks, it's basically a concatenation of linear and nonlinear functions, and this one has understood after basically going over it once or twice. But then the question is how to learn the parameters of a neural network, or how to learn the parameters of a support vector machine. And these things then use tools from optimization. Hence, there were also these optimization talks always at the machine learning summer school. And then things get a little bit more complicated, specifically if the optimization methods then for one machine learning method are discussed the one way and for another machine learning method the other way. And it's a little bit hard to get an overall and clear picture. So the motivation then to discuss optimization up front is basically also to introduce them at one point together, and then for the different methods that we discuss, only always reference them, maybe make here and there some particular remarks, for example, how a gradient is computed, or analytically, or whether it's, or for example, for neural networks, backpropagation is all about computing the gradient. So there might still be subtle differences in terms of optimization methods between the machine learning methods that we discussed. Nevertheless, they all fall then under the big topic of optimization methods. So today, or at least maybe not the full thing today, but when we now discuss optimization, the main thing is to introduce basic principles of optimization, and then to introduce things that you definitely have heard of before: gradient descent and Newton descent. And we will need these things essentially for the remainder of the course, except for PCA, because in PCA we basically need a lot of linear algebra, and we will leave it at that. But for all other topics, we will always reference and need optimization approaches. And for example, in LDA, it will be quite similar to the GLM parameter optimization that we learned about. So this will be analytically. But then for logistic regression and neural networks, we will need gradient descent. For these Gaussian models and variational autoencoders, one usually also can get quite far with gradient descent and Newton descent. In support vector machines, we will actually have to, because a big part of support vector machines is this relation to kernel methods, and this relation to kernel methods one can only really understand, or this development of kernel methods, if one understands a little bit more about optimization, namely constraint quadratic programming. So in a way, the optimization part in machine learning or data science is the thing that usually creates the most headache if you are studying something, because you feel you understood the model, but you didn't quite feel that you understood how the parameters are estimated. If one treats this whole thing as a topic on its own, then things are actually a lot more straightforward. So that's the motivation, and I will then always refer back to the optimization part. The introduction to optimization that I'm presenting here is completely based on chapters 2 and 12, and particularly today chapter 2 of the book by Nussedel and Wright, which I also have here. That's the book, which is a very good book for to get started in numerical optimization. So these are books on optimization that I really highly recommend. So personally, I find this Nussedel book the clearest and best, or at least compared to the convex optimization book by Boyd and Vandenberger. It's a very good book. It's mathematical, but it's also very intuitive, which is this whole thing about optimization. It's in a way one has a very clear intuition about what's going on, and the mathematics is not it's not that heavy somehow, but it needs to be clear so that one can understand what's going on, and that's really achieved in this book. A new book that I found recently is this Algorithms for Optimization. I've only looked into it a little bit here and there. What's nice in there is that it's a little bit an update, because with the machine learning and artificial intelligence hype over the last 10 years, there have also been some developments and novel applications and so on, novel stuff in optimization, and these are of course then included here. So I think it's also a very good book. So this Algorithms for Optimization. This is also a very good book, but that's doesn't really work that much as an introduction. So this relates to all the optimization code that Boyd and Vandenberger have implemented in Python. It's very good, but it's also it's fairly advanced, and the basics are maybe not as well established in this book as in this book, but it's definitely also a very good resource. So these are books on optimization. So the plan or what we need to cover in optimization is, on the one hand, unconstrained optimization, which we're going to start right now. In addition to unconstrained optimization, there's something called constraint optimization, where you try to find parameters that, or values or function inputs that not only optimize a certain function, but also fulfill additional side criteria, for example, that they are not higher than some value or something like that. And we will need that in particular for support vector machines. And otherwise, we don't need it much during the course. So, but in support vector machines, we really need it a lot to introduce kernel methods. And hence, I will introduce constraint optimization together with support vector machines. However, also what one learns the things in foundation in constraint optimization are, of course, fairly much based on what one learns in unconstrained optimization. So this is, of course, hierarchically related to this. So we need this in any case. Also, if we talk about support vector machines and constraint optimization, then. Good. So then let's start with some foundations in unconstrained optimization. So the basic problem in optimization is to find values or parameter values or input arguments of a function that maximize a certain function. So that's the whole point. So optimization means you have a function and you try to find the maximum of this function or the minimum of the function. with respect to its input arguments. So that's the whole thing, and we will now kind of formalize that in a way, however, you already know what's going on. So maybe I should have brought up this slide. So optimization in machine learning and statistics usually refers to parameter learning and estimation, and parameter learning usually implies the minimization or maximization of objective functions. So think of maximum likelihood principle in statistics. Maximum likelihood principle means you write down the log likelihood function of data, so the probability of data viewed as a function of the parameters, and then you try to find the parameters that maximize this log likelihood function. And there your objective function is the log likelihood function, and you try to maximize it with respect to the parameters. So that's a central task in statistics, and you already know that. In machine learning, usually or often the objective functions are actually less complex than the ones that you know from statistics, because they often don't involve any probabilistic terms. So for example, least squares minimization, which you might also know from undergrad statistics, which is probability free, is something that is also that's heavily used in machine learning. For example, for neural network learning, there you have a objective function that is often something like a least squares cost function. It's always the same thing: objective function, cost function, whatever. You try to maximize or minimize that. Maybe minimize if it's an error function, maximize it if it's a gain function, but it's always happening. And what you also know already from school, because that's what you did in school in calculus, is that to find a minimum or maximum, you have to do something with the derivative of the function. And you know that the first derivative at the location of a function minimum is 0. If you think about the mathematical preliminaries and the first exam in statistical methods, that's all the stuff that you learned there. So, and things that you did in school. You also know that at the function's minimum, the second derivative is positive, and at the maximum, it's negative. We will mainly be interested in minimization. I will show you in a second why. But yeah, so you know already some conditions for function optimization. You know that it's related to the first derivative. The first derivative is 0. Then there's a maximum, minimum, or saddle point, and then you can use the second derivative to establish a little bit more. And this will not change. Yeah. So this is when we now talk about optimization and the different criteria. This is exactly still the thing that's happening. The only difference is that we formalize it a little bit more, if you want. But stay clear about the fact that this is really it's just a generalization, usually then also to multivariate settings, but it's really this stuff. And then this is basically something that you did in school and that we also did for maximum likelihood estimation in an analytical setting. But you also know that one can do things numerically. So the easiest thing that you can do is basically try out all possible parameters and look for the parameter or input values of a function that give you the function minimum. However, usually evaluating all of parameter space is a little bit costly. So what's then preferred is to have a method that automatically somehow finds parameter values that minimize the function. And these are these algorithms in optimizations, and they can proceed in different ways. So we will look at the gradient method that proceeds in the direction of steepest descent of a function, which is somewhat useful. And we will see Newton methods, which basically minimize an approximation to a function. Yeah, so and these are then the algorithms, and basically these algorithms do their stuff until these kind of criteria for a minimum are fulfilled. So usually you let an algorithm run until you find that the first derivative of the function is not changing anymore, and then you are at least sure that you are at a saddle point. And that if you have a function that is very well behaved, like a convex function, then you already know that you're at a global minimum. But that's the basic logic, and this is also stuff that I think you're familiar with already. And we will now look at a little bit more closely, a little bit more mathematically, but that's the basic story. Are there questions about this at this point? So the motivation for minimization, or the basic idea of optimization? I don't want this, sorry. I want this list. Do I get the list? Any questions at this point? No questions. Do not grid view. To know this view. To know this. Anyway, I think it's. This is what I want. So, any questions? No. Good. So then let's start to now actually cast everything in a more mathematical and clearer language that it then allows us to also implement things. So let's first discuss what we are dealing with here and what the target of this whole thing is. And these early slides today, they are really kind of repeats from the mathematical preliminaries. So usually what we want to address in machine learning is some kind of objective function that is a function of parameters of a machine learning model or of a statistical model, and these functions are just multivariate real-valued functions. So they take in vectors, which are usually then the parameters of a model, and these vectors maybe have n dimensions. So don't confuse this now with the GLM, and n is the number of data points and so on. So this is all new stuff now. So we are looking here at a multivariate real-valued function that takes an n-dimensional vector, often then the parameters of some statistical model, and return a single real value to that, which, for example, could be the an error summary that you get when comparing the current parameters and the data, and then evaluating the overall error. So we will, of course, see specific examples of these error functions later on. Now forget about that we are currently thinking about error functions and so on. Just think of a multivariate real-valued function. Yeah, so we have a multivariate real-valued function mapping vectors x to a real value fx. And what we need to assume here to kind of have a gradient and a Hessian, and to make the proofs that we are looking at for the different conditions for minima of functions in a second, make them work, is that we need to assume that this function is smooth, which means it's just continuous functions. It doesn't have any jumps in it, and it has a gradient and a Hessian that we can compute. So we can compute that. This is what I said. So the x later on typically model parameters, and f is typically an objective function. So let's see what is still on in your memory. So you already learned about the gradient and the Hessian. Does anyone remember what the gradient of such a function is, how it's defined? Josh, say. I think most of you actually, Tamer Salty, he knows what it is. Then tell us.
I think it's the vector of first order derivatives, partial derivatives.
Exactly. And the Hessian?
Second order derivatives.
Yeah, and it's the matrix of those. Exactly. So this is stuff that you've already seen in mathematical in the mathematical preliminaries. So I'm just showing you again here so that you are reminded of that. So the gradient of a multivariate real-valued function is a vector, and it's the vector of first-order partial derivatives. So you compute the derivative of this multivariate function with respect to each of its inputs, if each of the components of its input vector. In the mathematical preliminaries for last winter term, you find some examples for that. For example, if you have a function that is defined as f of x and y equals x squared plus y squared, then the derivative with respect to the first coordinate, so with respect to x, would be 2x, and the x squared would go away, and the derivative with respect to the second coordinate would be 2y, and then you have the gradient 2x, 2y, if I'm not mistaken. So that's the gradient. You also know what that is. The important thing that you also need to keep in mind always is, of course, that the gradient is just the generalization of the first derivative of a function, the first derivative of a function from a univariate real-valued function to these multivariate real-valued functions. By the way, there is also the first derivative of a multivariate vector-valued function, which I will not show here. Does anyone remember what that is called and what form it takes? So the first derivative of a multivariate vector-valued function? No? No one? No? Exactly. You can also just turn on your mic. Yes, it's the Jacobian. We will actually meet the Jacobian also at one point, but it's the Jacobian is not that important if we're talking about machine learning, and it's very important machine learning, but it's not that important if we're talking about parameter learning, because usually the cost or error or objective functions that are used in machine learning and statistics are real valued, meaning there's a scalar number coming out of them that quantifies the cost, and not vector values, so that there are multiple errors that you in some way want to minimize at the same time or something like that. So this is why when we talk about optimization, in first instance, the gradient is much more important than the Jacobian. And actually the Jacobian of multivariate real-valued function is just the transpose of the gradient. The Hessian is the matrix of second-order partial derivatives. So again, if we have this function x squared plus y squared, and we compute the second derivative, then of course the x and the y also go away, so it's constant. And the only thing that is a little bit, or is again and again confusing for the Hessian, is how the order is. But here. Here you have the derivative with respect to x1. Actually, I'm just seeing that there's actually a typo. It also should have a partial in between all of those. So you have the derivative with respect to the first coordinate, and then you have also the additional derivative with respect to the second, and so on. And you basically write all of them out in a matrix. So if again we have our 2x, then we would again compute the derivative with respect to x. So we would have 2 here, and then if we compute the derivative of 2x with respect to y, we would have nothing here, so we would have 0 here, if I'm not mistaken. But again, you find examples for that in the mathematical preliminaries. So that's the Hessian. Important thing is it's the second derivative. Yeah, it's the generalization of the second derivative to multivariate real-valued functions. Good. So that was the kind of a reminder of things that we've seen previously. So the point is now we want to first establish some criteria of how to find, or for finding the minima of multivariate real-valued functions, because we always have to do that in many machine learning and statistical methods. We have to find minima of functions, and a big help in that will be Taylor's theorem. Before I talk about Taylor's theorem, let me first give you the problem that we actually now want to deal with. So we are given such a multivariate real-valued function, and then an unconstrained minimization problem. So the center thing of what we're trying to do is the problem of finding the minimum of such a function with respect to the parameters. Yeah, these things are just these things, as I previously said. So now I'm trying to share a whiteboard to show you a little bit how to think about it. So, okay, I hope everybody can see a whiteboard now. If you don't see a whiteboard, say something. As I don't want. So apparently people can't see a whiteboard. So one way to think about this whole problem of minimization is, of course, to always think about it in terms of univariate functions, which is always helpful. So if this is typical univariate visualization, a coordinate system, then and this is some kind of function. Then the point is now to find the location of the minimum. So so this is now our function here, f, and we have our coordinate system x, and we try to find the minimum. And as you can see, at least if we only, so we not talk what might happen here. So sorry, you can't see this. We're not talking about what's happening on the other side of the vertical arrow here. So the minimum, obviously, if you look at this function, the minimum is obviously, oops, it's not the greatest whiteboard, but the minimum is obviously here. So that's that is min fx. Keep in mind that the minimum of a function is this value that the function takes, and it takes this minimum at a location that is called a minimizer. So that's the location here on the x-axis where the minimum is taken on. So a first thing is, why do we talk about minimization if we also want to do things like, for example, maximum likelihood? And the point there is that minimization, that maximization of a function is the same as minimizing the negative of a function. So we can essentially always turn a function around and then do maximization. So if we want to find the maximum of this function, which you can also see, it's the same as doing minimizing the negative of f, and this is what I wanted to draw here. So if you take the negative of f, so you just put a negative sign in front of f, then you would get something like this. So you just basically mirror things on the x-axis, and then, so it's not completely awesomely drawn, you see that where you have the maximum of this red f, you have the minimum of minus f. So the blue one now is so already respecting my colors. Yeah, that's good. The blue one is minus f of x. Yeah, so it suffices. Oops, now I changed the colors. Anyway, sorry. It suffices to consider minimization, because if you want to do maximization, you can always minimize the negative of a function that you want to maximize, which is actually happening when you do, for example, maximum likelihood estimation in kind of cognitive modeling. You usually have tools for minimization, like F-min search in MATLAB, and then you take the negative log likelihood function. Yeah, so that's one point. And now I want to go back to my other screen. So this is this point. So minimization suffices, and that's the whole point. Yeah, good. Questions about this general problem and the question about maximization versus minimization? I thought there was something in the chat, but maybe there wasn't. Good. Now, the first thing that one needs to ask oneself is when does, or what are criteria, what are conditions that a function actually takes on a minimum? And these are these first order. Can you see? You don't see slides right now? Okay, that's strange, but I changed nevertheless. So can you see slides again now? Yeah, okay. The question is, or maybe let's do the other thing first before we talk about the conditions. Let's first introduce the notion of minimizers, because we already have seen them briefly. Can you briefly, you saw my drawing, right? Can you in the chat just put in yes if you saw my drawing? Good, thank you. Where I showed you also the minimizing values, and here this is just cast a little bit more formally. So again, if you have a function f, then x star is called a global minimizer of f if f of x star is smaller or equal than fx for all x. So this would be over the entire input space. And then, of course, you can have local minima. And of course, you're all aware in terms of parameter learning and so on, isn't always the problem that you get stuck in a local minimum. So everybody knows about local minima. If one casts that a little bit more formally, that means there's at least a neighborhood of x such that of x star, such that the value that the function takes at fx star is smaller than fx, but it doesn't need to be over the entire input space. And then one can make this more strict by saying, okay, because these global minimum and local minima are not necessarily unique, but so this function minimum can be taken on for multiple values, and if you want them to be unique, then or if you think about strict localizers, then they need to be really smaller, not smaller than equal than some fx. So these are the formal definitions of the minimizers. Let me again go back to the drawing board. So if you don't see, now you should see again an empty drawing board. Nice. I hoped I would get back to what I've drew before. But again, now if you have a function in terms of local and and so this is now a function again, and these are the coordinate systems now drawn by hand. Here you obviously see that you have multiple minima, and if you only look at the function where we see it, then you also see that we have a global minimum here and because that's really the minimum across what we are looking here, but we have another minimum here. So you would, both of them are local minima, but this is local minimum is also the global minimum. Yeah, and so that's that in terms of minima. Now we go back here. And then the main thing in terms of optimization is first to establish some conditions to identify minima. And these conditions are the conditions that you know from school. So, for example, at the location of a minimum or a maximum, the first derivative is 0, which of course you can also always kind of verify if you look at the function. So let's again switch to the whiteboard. Maybe it's because I go to a new whiteboard. This is what I should do. There we are back. We have one whiteboard. Of course, the derivative is 0 because here you see that you need the cursors, right? Here you see that the function is first increasing, and then if it's at the location of its maximum, it's not further increasing, but it's also not immediately decreasing. So the rate of change of this function is 0. So you know that if the derivative is 0, then there can be a minimum, can also be a maximum, and can also be a saddle point. Now on the slides, and this is what the slides are then all about, is that from these kind of things, that at the location of a minimum, the first derivative is 0. On the slides, they are all, of course, framed first of all for multivariate real-valued functions. So here, for example, in the terms of the first order necessary condition, x star is a local minimizer of f. If x of star is a local minimizer of f, so if we are at the location of a minimum, then the gradient of f is 0. Yeah, so instead of talking about the first derivative, we talk about the gradient. So that's, of course, a difference compared to what you might have been used to from school. And the other nice thing, and this is what so these first order necessary and second order necessary conditions, of course, one has heard a lot, but usually they are kind of intuitively discussed, like I just shown you, but they are not formally proven. And in the Nuttall and Wright chapter on numerical optimization, all of these conditions are derived fairly concisely in these proofs that I also include here. Now, all of these proofs, so we have the first order necessary condition, we have the second order necessary condition that states that if x star is a local minimizer of f and the Hessian exists, then the gradient is 0 and the Hessian is positive semi-definite, which is the same thing as saying that the second derivative is positive. And then also the sufficient conditions, so that if actually this holds, so if you have the gradient to be 0 and the Hessian to be positive definite, then you find a local minimizer. So the necessary and sufficient conditions that are also discussed in the mathematical preliminaries, long sentence, all of these conditions are proven very concisely. And that's what is really nice. So there's a formal justification for that. And these are these proofs. And all of these proofs are based on what I have here, namely Taylor's theorem, or better, the mean value theorem form of Taylor's theorem. So to understand the proofs of the first order and second order necessary conditions, so to understand why they hold, and especially why they hold in the multivariate setting, Nuttall and Wright always reference and make use of Taylor's theory. So so instead of going over all the individual proofs there right now, and I think in general in the lecture, so you can read them and hopefully understand them, so that you know why these things hold. Of course, it's more important for the exam, and for practical purposes, it's more important to know that these conditions exist. But for a real understanding of these conditions, it's of course helpful to look at the proof. But for this proof, you need to understand this form of Taylor's theory. And this is then the last thing that I want to briefly discuss. So all these proofs make use of Taylor's theorem. At least that's what Nuttall and White say. They are a little bit cheeky there, because what they present as Taylor's theorem is, from my perspective, it's actually more the mean value theorem and the second order mean value theorem. So what they say and state without proof is that the following holds. If you have a multivariate real valued function, then it holds that if you that you basically can the value of this function at some point away from x, namely at the point x plus p for some other input vector, corresponds to the value of f at the location x plus the gradient or the first derivative of x at some location between x and p times p. So this looks quite a lot like a first order Taylor approximation. However, in a first order Taylor approximation, it's a little bit different, because you would have the derivative at the location x, and you would also, of course, be aware that there's an error. And this would not be an equality, but it would be an approximation. So this is so if you think about Taylor's theorem, which you also learned in the mathematical preliminaries, this looks like a first order Taylor. This looks like an exact first order Taylor approximation. And this is essentially also what it is. The same thing here. This then goes to second order. The question is, what does this really want to say, and where does it come from? So let me show you what this wants to say by again going back to the whiteboard. Share content. Oh, okay. You're sharing your screen. It's a little bit. It's not completely awesome, because you can only get to, or somehow you can get back to sharing a whiteboard by sharing a new whiteboard and never going back to my original whiteboard. That's also a nice whiteboard. This is also a nice whiteboard. Okay, so what is this with the Taylor theorem, which is the basic for all of these proofs? This wants to say the following. If you have a function, again, we assume the univariate real valued case, then this thing that we see there, that's good enough, says the following. So here, let's say we first consider this linear approximation, this thing. So this would be what on this slide was called nabla, but we can just do it like this. Oops, f of x plus tp p. So that's this. Now let's go to, let's have the function as well. So this would be our function. That's the function f. And then we have f at the location x. So this here. So it's a little bit off, but this would be f of x. So what you have on the x-axis is x, and what you have here on the x-axis is p. So text, so this is x, this is p. And now what this Taylor theorem is saying, that you can compute the value of f at the location fx plus p. So at this location, by using this thing here plus so what it's saying is that fx plus p equals fx plus the derivative of f at some location fx t times p. And what this means, and this t, so this is the important thing, this t is in the element, in the interval between x and p. So what this wants to say is that at one point between x and p, the derivative of x takes on the value that corresponds to this slope. So you can find a t such that this holds. You don't know where this t is, but you can always find a t like this. And the point here is, of course, here it's not the case, because here at this location of x plus tp, the derivative does not work for constructing fx plus p, but at this location, so roughly here, it actually works. So that's the mean value theorem, so that this value t always exists. And what they did is to basically express the mean value theorem in terms of Taylor's, or in looking like a Taylor approximation. And this is the basic for all the proofs that they use to show why these necessary and sufficient conditions for minima hold. So this is why I'm talking about it and making a bit of a fuss about it. Good. So my presentation here is based on the second chapter of the Not to Die and Write book. And as I said last time, this new book on algorithms for optimization is kind of a modern take on the whole thing. So it's also very nice. So I really recommend it. And whenever you get lost in some machine learning technique, it's usually because the machine learning book doesn't explain the optimization method that well. So then I highly recommend that you look into these books. Good. So last time we started with foundations of unconstrained optimization and discussed some definitions and algorithms. These foundations of constraint optimization we will actually visit only when we discuss support vector machines, because that's when we really need them. And last time we already discussed that, and also today, that a central task of machine learning is parameter learning. That parameter learning usually implies the minimization of objective functions. I mentioned that earlier today. And then we discussed some criteria for finding solutions, or for solutions in optimization problems, and these are these criteria that you know from school. At a function's minimum, its first derivative is 0. That's how you find minima in school math or high school math all the time. And also then checking the second derivative will help you to evaluate whether it's really a minimum. And we basically mentioned last time that learning algorithms identify parameters for which these minimum conditions hold, and we mentioned two important forms of learning methods, namely gradient methods and Newton methods, but we haven't discussed them yet, so I just mentioned them like I did now last time, and this will be the main topic for today's session on optimization, then to discuss gradient and Newton methods. What we've seen also last time is that the main objective function that we are dealing with is of multivariate real-valued form. So it takes in n-dimensional vectors and returns a single scalar value. The single scalar value is then the, however you want to call it, the loss value, the cost value that you're trying to minimize, or if you're doing maximum likelihood, the log likelihood value that you're trying to maximize. And we also discussed certain aspects of these or certain other features that you can compute on multivariate real-valued functions, such as the gradient, so the vector, the column vector of the first partial derivatives, and the Hessian matrix, so the square matrix of the second order partial derivatives. And then I introduced this Taylor's theorem in its mean value theorem form. The reason being that this, for the conditions for minima, is kind of the basic tool that is used in all of the proofs. And we discussed a little bit about this. So remember what it says. We will need it today again for when we discuss the gradient method. So I'm bringing it up here again. So again, think about that if f is a multivariate real-valued function, and you're trying to compute f at the location x plus p, where p is kind of the step that you take from x, then you can express the value f at x plus p as the sum of the value of f at x and the product of the gradient of the function f at a location x plus tp, where t is 0.1. So sorry, it's not 0.1. T is in the open interval 0 to 1. So you are here with a gradient at some location between x and x plus p. And this multiplied by p gives you the value at x plus p for the function f. And we stated that this is essentially the mean value theorem. I gave you a link to a YouTube tutorial which explains this in a lot of detail. So if you're not quite happy with that, and also not with the mean value theorem, have a look at that. But this is kind of the analysis background we assume as given. We also saw the higher order form where you express x plus p as the sum of the value of f at x, then the product of the gradient and this step vector p, and the Hessian matrix multiplied with the square of p, and the Hessian matrix again being evaluated at some location between x and x plus p. And in the very end we had some discussion about this, and I was a little bit confused, but so the point is just that that we consider 2 points, x and x plus p, and then x plus tp for t being in the open interval 0.1 is just some point between x and x plus p in the direction that you go from x to x plus p. So mainly this is needed for these proofs for the minimum and conditions. But as I said, we will see it in a second again when we talk about gradient descent. And then to summarize the main points of these ideas of describing solutions to optimization problems, I now make the summary slide. So in general, we consider the problem of minimizing a function f with regard to its n-dimensional input x, which we've seen is the same as maximizing the negative of this function. So this then allows to only consider minimization all the time, because if we want to maximize a function, we would just minimize the negative of the function that we want to maximize. So for example, in maximum likelihood, we want to maximize the log likelihood function, so we can equally as well minimize the negative log likelihood function. And we discussed a little bit in detail that there are different forms of minimizers. So values x star for which the function takes on a minimum. And we discussed that there are things like global minima, so which is really the minimum over an entire space that one considers. Of course, it always depends a little bit whether it's a global minimum on the space that one considers to be the global space. And then the notions of local minimizers, which I brought up here. So where the function, where the value of the function f at location x star is smaller or equal than the value of the function at location x in all x which form a neighborhood of x. So essentially, around x. So this neighborhood is the neighborhood is with respect to x star, and this is essentially what we use. You can make it stricter by requiring full smaller than, so as to come up with a strict localizer. Usually the algorithms identify locations where the first derivative is 0, and then you cannot, you never are really sure whether you find a strict local minimizer or just a local minimizer, and definitely you never know unless you know that your function is convex, in which case a local minimizer is also a global minimizer, but you're never sure whether you really found the global minimum. So these kind of mathematically strict definitions of different minimizers are interesting from a theoretical perspective. From a practical perspective, essentially these algorithms not necessarily check whether it's now a local strict minimizer or a local minimizer or global minimizer. Then we discussed the first order necessary condition for a minimum, which or a minimizer. So always, so minimizers and minimums are of course different things. So the minimum is the value of the function that is taken on at the location of a minimizer. But the first order necessary condition for a minimizer here is if x star is a minimizer of f, then at the location of x star the gradient of f is 0. Of course, the 0 refers to a vector if this is a vector. So all components of the gradient vector are 0. This is what is meant here. Then there is the second order necessary condition that if there is a location, if x star is a minimizer of f, then the gradient at x star is 0. And there's the first typo for today. And the Hessian at x star, not at x, but at x star, is positive semi-definite. And then there is the second order sufficient condition. If at some location x star the gradient is 0, and at the location x star, that's the same typo because it's a copy and paste error, the Hessian is positive definite, then there is a minimum at x star. Yeah, so in principle, I think you know these conditions, And what I also want to point out here is that if you think about the mathematical preliminaries, I also included now the mathematical preliminaries again on the website of this course, because you always need them. If you think about the mathematical preliminaries, there's quite some discussion of these necessary and sufficient conditions and the relationship between the function itself, the first derivative and the second derivative, and the minimizer in the mathematical preliminaries. And this is just a picture there where I discuss these topics in some detail for the sine function, for x minus 1 square, and for minus x square. Yeah? And the logic is, of course, exactly the same if you go to multivariate real-valued functions, only that, of course, it gets a little bit more complex. And then the nice thing, again, in the slides, which I basically, of course, got from the Not So Darn Right book, is that there's not only the mention of these things that you are familiar with from school and that you have used, but there are also proofs of why this is. Yeah, I mean, it's easy to see that this holds. So, for example, if you look at this function here, x minus 1 square, which has its minimum at 1, and this function is this blue 1, and you plot the first derivative of it, then you see that at the location of the minimum, the first derivative is 0, and you see that the second derivative is always 2, so it's always positive, so you have a minimum. Yeah, but yeah, these kind of things you know, but make yourself aware of them again, and don't be afraid of the fact that they now occur for functions that not only take a scalar argument but take multiple arguments, so n-dimensional vectors. Good. Regarding these definitions and characterizations of solutions, are there any questions? Okay, there don't seem to be any questions. So then let's go now into what we are mainly interested in, of course, in machine learning, namely the algorithms that allow us to identify these minima. And algorithms and optimization are characterized by a general form. And this is shown here. So the first thing in an algorithm is, and what also characterizes numerical algorithms for optimization, is that you have to select a starting point. And this is referred to as initialization. You have to define a starting point, which is your first guess of what the minimum could be. But of course, usually you don't have much information about this, and you just choose a starting point in a way arbitrarily. So I denote the starting point here as x0. It's of course an n-dimensional vector because we are minimizing the function with respect to these n-dimensional vectors. And yeah, there are no real rules of how to define a starting point. One thing that you can do if you use numerical optimization is try different starting points, doing different minimization, and see whether you will end up at the same location, which is usually a good sign, so that your objective function is relatively well behaved, and that irrespective of where you seed your parameter, you recover the same minimum. However, sometimes this is not really possible, because if your minimization takes really a long time, then doing it over and over again takes a lot of time, so you might not do it. There are some people say you can randomly assign a starting point. I think one thing that is important is to make sure that if you assign a starting point, that you check whether the algorithm actually moved from your starting point, because if it doesn't move at all from your starting point, then it's usually a sign that you're in a very flat region of your objective function, and then you might look around a little bit in terms of your starting point to see whether you can give it a better starting point, so that you then actually see some minimization at least. So initialization and the choice of a starting point always needs to be there. So there is not a magic algorithm that starts without some initial value. It doesn't exist. After the initial starting point, there follow what is referred to as iterations. For a number of times, the same procedure is applied, if you will. And of course, everything that is on this slide and everything that we discussed with respect to algorithms is very closely related to the computer implementation. And if we talk about iterations here, then of course this is very closely related to what you know from programming as control flows, so while and for loops. And this is, of course, the idea here. Now, the iterations are numbered, and there's this iteration counter, which I take where I take the variable or the letter k for. And then based on this letter k, there are what is referred to as iterants. So the values of the parameter or the argument of your objective function x is now subscripted by the iteration counter. So these values change, and the first thing that you do is that you evaluate xk plus 1 based on information about f at xk. Yeah. So think about the logic here. You start with x0, and then you evaluate x1 because your k is 0, x1 based on information about f at x0. So you do something with f and x0. What you do that will, depends on the method, and we will see that. So you evaluate x1, and then you use the information of f at x1 to evaluate x2, and so on. And then so you get a sequence of parameter values, or parameter iterants, or arguments of your objective functions, iterants, that goes on as long as you let it go on. And at one point, because at one point you want to be finished, you stop this procedure, and then you either have some criterion that tells you that the iterant has now approximated a minimizer, for example, because the gradient is 0, so this is why you need these necessary and sufficient conditions, and we will see that later on. This is the typical convergence criterion. If the gradient is 0, then you stop, or you stop if somehow there's no progress anymore. So in terms of convergence criteria, that really depends on different algorithms. So one thing to check is, of course, also if the function f is still decreasing. If it's not decreasing anymore, then you might as well stop. So that really depends on algorithm to algorithm. Another criterion for stopping is just that the number of maximum iterations has been spent. So even if there is still a little bit of progress, but it might be small, at one point you want to stop the algorithm. So the rules for stopping the algorithm are as kind of flexible as the rules for selecting starting points. So in the end, if you use some method that somebody has implemented, it makes sense to at least know when this algorithm is stopping, and maybe change the stopping rules if you think it's not really doing what it should. That's the general form. So I think it's fairly straightforward. So you create a sequence of parameter iterants that step by step hopefully get you closer to a minimizer of your function f. The question is now, how do you actually compute this xk plus 1 based on xk? And there are now two basic forms of algorithms that we want to discuss, namely gradient descent and Newton descent. And you might have heard about gradient descent in your favorite deep learning neural networks courses, because that's what neural networks usually refer to, but gradient descent is not somehow linked to neural networks. Gradient descent is a very general technique, and it's just one application in neural networks. So the general form of gradient descent is as follows. You choose an initial value for your minimization algorithm. You choose a learning rate, alpha, which is a scalar value, and what it does we will see in a second. And you choose a convergence criteria, delta, which is also positive. And then you do the following. So for these iterations, you compute xk plus 1 based on xk. So you set xk plus 1 to xk. So for example, if your x0 is, let's say, 2, then you at iteration 1 you put here 2, and you subtract something from it. And what you subtract is the product of the learning rate and the gradient of the function f at the location xk. So always keep in mind that xk, and then of course xk plus 1 as well, can be n-dimensional. So for example, if this is a two-dimensional vector, something like 3, 1, then you would start here with a 3, 1, and then you would subtract from it alpha times this gradient vector, this two-dimensional gradient vector, which you evaluated at xk. Yeah? And then yeah, just a second, let me just finish this, and then we do questions. So that's the update rule. And then you check if your gradient, and maybe, so this is also maybe not that nice, maybe I should put here the norm of it. So if the norm of the gradient, so the length of the gradient vector, is smaller than delta, or you understand this is a vector, you can of course also check for every component of the vector. If this is smaller than some value larger than the 0, then go to 1. That's definitely the second. If I count the Hessian as just one typo, then this is the second typo. This should be, of course, go to 1 again. Good. So there was a question.
Hi. Sorry. I was just wondering, in the first, like for xk plus 1, why are we subtracting from xk? In the hello?
Yeah. So why are we doing this?
Why are we subtracting? Because the intuition would be to add. I don't know.
Yeah, so that's a good question, and we haven't answered it yet. So I'm just telling you that this is how what gradient descent does, but I haven't told you why we're doing it like this. And this is what actually the next slide is about. What we are doing is we have some parameter value, and then we subtract a scalar multiple of the gradient vector from it. And the question is, of course, like Saloni asked, why are we doing this? So in a way, it makes sense to do at least something. So it makes sense that if we have xk and at xk there is not a minimum yet, then that we change xk. And one way to change xk is to add something to xk or to subtract something from xk. But the question is, of course, what? And what gradient descent says is you subtract from it the gradient at location xk. Now the question is why? And this is, I put it here in a theorem form. This is the motivation for using gradient descent. So if you have a function f, which is a multivariate real-valued function, and you have some value xk, then the gradient direction, so pgk, which is not the alpha, but this part here, minus the gradient at xk, is the direction of steepest descent of f in xk. So if you go in parameter space from xk in the direction of p, or better now pgk, so in the direction of the negative gradient, then in terms of the function value, you go in the direction of steepest descent. So you can really think about that you are kind of in the mountains and you stand somewhere on a hill, and then you look around in which where you want to go. And if you want to make sure that you are off the mountain as quickly as possible, one idea is to go where the descent or the slope of your mountain is steepest, and you go in this direction. What you need to keep in mind is that this is not the only direction. So the gradient direction is not the only direction that you can go from some point on this mountain. You actually favor this direction of the gradient, because in this direction the descent is steepest. And why this is steepest, we will see on the next slide. What is important when we now talk about comparing different directions, because you could basically go in all directions around the circle, but you're going into the direction of the gradient. The important thing is we're talking only about the direction. How far we go into this direction depends on the learning rate. Yeah, so we might as well talk about unit length of this gradient vector, and then by alpha we can scale how far we go into the direction of steepest descent. So and this alpha is actually fairly crucial. Although the gradient direction says it's steepest descent, going in this direction not necessarily ensures that you really make a big progress towards the goal of the minimum, because, for example, if alpha is very small, then if you stand on the hill and you go into the direction of steepest descent, you might just go like one step into this direction, and then you're still on the hill if you just went for one physical step. Another thing is that if you want to, from your location in the mountains, go to the lowest point possible, if you go into the direction of steepest descent, but you make a very large leap, you might end up on the next hill, and then you're still not completely down. The steepest descent direction is a good idea, it's a good heuristic, but that you really make good progress towards your goal of reaching a minimum, that also heavily depends on alpha. But now the next question that we want to answer is why is the gradient the direction of steepest descent? Because that's, I mean, we know what the gradient is. It's the vector of first partial derivatives. But why should this be now steepest? I mean, I think that from just knowing that it's a vector of partial derivatives, there's nothing in it that says that this is now steepest descent in terms of the function f. And this can be shown as follows, based on what the Notzdal and Wright people do. So again, this requires Taylor's theorem in this second order form. So we consider the value of the function f at xk plus some step p multiplied by some step size parameter alpha. And we can write this according to the second order Taylor theorem in mean value form as the value of the function f at xk plus alpha p times the gradient at xk plus 1/2 p square times the Hessian at xk plus tp, where t is somewhere between 0 and alpha. So if you remember the slide from earlier, the alpha was 1 there, so the t was between 0 and 1, and now we can either go shorter than 1 or larger than 1. So this is just, again, Taylor's theorem. Now, one important thing to realize about this is the rate of change, and we want to talk about rate of change when we talk about steepest descent. The rate of change in f along the direction p is the coefficient of alpha here. And this coefficient of alpha is this expression, namely the product of the step direction and the gradient of f at location xk. So the way I think about it is that if you think of x as position, then of course x the position is given by the product of time and velocity. So it's kind of the first order term in time, and time, so how long you do this, is now this alpha parameter. Yeah. So the point in this proof is that if we talk about steepest descent, we want to look at the rate of change of f, and this rate of change of f is encoded in this p times the gradient of f in xk term. That's how this argument works. And higher order effects of time, so how fast the velocity is changing, so acceleration, this thing here is ignored because we are only interested in the rate of change, so the descent. So we focus on this term now. And the thing is, of course, we want to make a steepest descent, so we want to have to minimize this value. Of course, minimize in terms of also going into the negative direction, so not minimize until we are at 0, because then nothing happens anymore, but minimize this into some negative direction, so that the value of f actually decreases. We are considering the unit direction because we want a fair comparison. So if we are going into different directions, we want to multiply the direction of unit length with our alpha, so that it's actually a fair comparison between the different directions. And hence we're trying to minimize this term subject to the fact that the norm, so the length of this vector p is 1. So that's the aim. It's actually a constraint optimization problem, which we haven't really discussed, but we will be able to deal with it. It's in this case not that complicated. Now the question is, how can we minimize that? And this can be minimized by thinking about what this means. So we have a dot product here, and you hopefully know that vector dot products can be, of course, referred somehow to the relationship of the vectors. So if you have two vectors, x and y, and you multiply them, and the dot product, or the dot product or scalar product, it's the same thing. The dot product is 0, then you know that these two values are orthogonal. Yeah, so that's one thing that you know. So somehow the I think that's some basic vector calculus, which I hope you're familiar with, so that you can express dot products also in terms of the norms of these vectors times the cosine function. Yeah, so this formula is just how you compute the angle between two vectors based on the vector components, and this is the formula for that. If you're not happy with that, look up angle between two vectors or something like this, and then you find exactly this formula. Now, one thing that we know in this formula is that the length of the vector p is 1. So we can already take out this norm here, and then just look at the gradient norm. And so then we end up with this. The gradient norm, the length of the gradient is, of course, something positive, and the cosine function just varies between -1 and 1. And then, of course, the smallest value that you can get here is, because this doesn't depend on p anymore, the smallest value that you can get is that the cosine of the angle between p and the gradient assumes the value -1, because that's the smallest value that a cosine function can take on. But this means, so if you think about it, if you have orthogonal vectors, the cosine of this is 0. So if you, if your cosine is -1, then the value of p must be exactly anti-parallel to the gradient and of unit length. Yeah, so so you look at this thing, you want to make it in such a way that the cosine between these two vectors is -1, which implies that p and the gradient are exactly antiparallel. And antiparallel means that p is equal to minus the gradient, and then you need to make sure that you respect this constraint. So if you then divide by the norm of the gradient, then you have normalized this. So the unit direction that you that minimizes this optimization problem is exactly the negative gradient. Yeah, and this motivates why this is the direction of steepest descent. Of course, in this form, it's not normalized, so this is just the gradient, so this is not necessarily of unit length. But then, of course, because you scaled it by alpha, you can either make it shorter than 1 or equal to 1 or larger than 1. Only for comparing different directions, it's more useful to normalize this. So this is why in this proof we end up with the minimizing direction being normalized. So that's one argument how you can show that the gradient direction, so minus the gradient at location xk, is actually the direction of steepest descent. It's not quite trivial. Yeah. So I think this this is an argument. Yeah. It's you can find other arguments. Usually these arguments are not discussed. Usually what you find is just this result. So the gradient direction is the direction of steepest descent. And there are different ways to show that. One way I've just shown you. And of course it's important to remember that the gradient direction is the direction of steepest descent because that's a heuristic motivating gradient descent. But to show that it's actually the steepest direction, I think this is a fairly straightforward way to show it, but it's still a little bit more involved than just saying it is the steepest descent. Good. Questions about this relationship between essentially this update rule and steepest descent? Okay, no question. Yeah?
I'm sorry, I don't know if this is relevant, but so and this argument will also hold true for oscillations and waves and
for what?
For oscillations like a pendulum movement or a wave, if we are into creating an algorithm or in a condition where
the question doesn't really make sense. So you're talking about oscillations, so that the parameters oscillate?
Yeah, because not the parameters, but if there is a state where things are oscillatory, or there is
what is oscillatory?
The minima and maxima are switching. So the
what? Minima and maxima are not switching. They are at a specific location for a given function.
Okay, I take back my question. Look, my thing is the steepest descent would also sometimes be in a condition where it's changing a direction, right? It doesn't always have to.
That's true. Yeah.
Always.
No, wait, the steepest descent, if you're at a given location, then the steepest descent is in one direction.
Always.
If you go if you go to the next location, then the steepest descent might again point in a different direction.
Depending on the iterations, it can change direction.
Yeah, of course. Yeah. I mean, it's the direction of steepest descent on a given iteration.
Yeah. Okay.
Because it's always the gradient evaluated at location xk, and if you are at a next iteration, then you have a different gradient and you might go in a completely different direction. So yeah.
Okay, thank you.
Good. So before the first break and then before the second hour talking about Newton descent, there is a generalization of gradient descent, which is referred to as line search method. So gradient descent, in a way, is a specific line search method, and there are many line search methods for optimization. So let me briefly talk you through the algorithm for line search methods. So that's now a generalization of gradient descent. So again, you choose an initial value x0. And then you choose a descent direction. So in gradient descent, you always go into the direction of steepest descent, but you might have also reasons not go into the direction of steepest descent. If, for example, if you go a little bit to the left of it, but with a fixed step size, then you might minimize more or whatever. So gradient descent is just one descent direction that you can do. And then the important thing, and this is usually what is not done in this very basic gradient descent, is that you have to think about the learning rate. And ideally, at least a good way to do it, to have an adaptive learning rate that actually figures out how far to go into the direction pk. is sensible. So you try to find an alpha k which minimizes the value of the function in the direction alpha pk. And then, so from my own work, for example, with regards to variational inference and minimization of the negative variational free energy, if on a given iteration you actually also solve this minimization problem, then it's much more reliable and you actually can make a better progress. Of course, that means that within each iteration you solve another minimization problem, which also takes time. So of course these algorithms are a little bit slower if you use adaptive learning rates, and then you define your new parameter value xk plus 1 as xk plus this adaptive learning rate plus your this adaptive learning rate times your descent direction. So again, you go into the direction of the descent. Again, if you want to do gradient descent, you would go into the direction of the negative gradient. So you would have minus nabla fxk here. So my personal view on this, and also with the experience on this, is that a gradient descent with a fixed learning rate is usually not really working that well. With adaptive learning rates, it's usually going okay. So, and then in the last step, you would do some convergence assessment. If you haven't achieved that, you would again choose a descent direction. Yeah, so this is the general set of line search methods, and if you look into the books, you will find that there are many different line search methods, and in the end it makes sense to tailor a specific optimization problem to a specific optimization method to a specific problem. But the first big group of optimization algorithms that we've now discussed is gradient descent as a special case of line search methods.
Then let's continue. So we talked about gradient descent as a special form of a line search method. And so there are many variants of line search methods and many ways one can tailor these approaches to specific problems. Now the second big group of algorithms that are used for optimization are algorithms based on Newton descent. And Newton descent is also just an optimization algorithm. But it's different from gradient descent, hence Newton descent, and will be discussed now. So again, it starts with some initialization, like all learning algorithms or all optimization algorithms, with some x0 and the choice of a convergence criterion. And then it proceeds as follows. It also is based on iterations, of course, but, and that's the crucial thing, the update rule here, this rule for computing the iterand at k plus 1 based on xk is different than in gradient descent, as you can already see. So what do we have? We have the iterand at iteration k plus 1. So the value of the parameter at k plus 1 is computed by taking the value of the parameter or the iterand at xk, and then you subtract from it the gradient, but in this case you multiply the gradient with the inverse of the Hessian matrix at location xk. And as you can also see, there is not really or there is no learning parameter here. If you want, you can of course interpret this multiplication of the Hessian matrix, of the inverse of the Hessian matrix as the length adaptation of the gradient vector. And the question is then why this multiplication with the Hessian. So that's the update rule, and then of course, like in any algorithm, again, you check whether the gradient is going to 0, and if it's 0, then you hope you're at a minimum and stop the algorithm, and of course here then you go to 1 again. So the question is, what about this Newton direction? So why is it not only maybe a good idea to go into the gradient direction, which is the direction of steepest descent, but why is another thing that you can do doing this kind of update? Now, this can be motivated as follows. The basic idea is that you minimize not f itself at the kth iteration, but a model of f at the kth iteration. And this model function, so mk, is the second order Taylor approximation of f in xk. So this is now a real Taylor approximation, not this mean value theorem, but it's a second order Taylor approximation, which is of course only correct for quadratic functions. If you have more complex functions, then of course the Taylor approximation of f will always make some error. So you have a function f, and you, instead of minimizing a function f at the kth iteration, you minimize the second order Taylor approximation, and second order Taylor approximation, just the usual thing. So in xk, so you evaluate the second order Taylor approximation in xk, so you take the value of f at location xk. To it you add the gradient evaluated at xk times the point where you want to evaluate this model function, and you take the second order term where you have the square of the point where you want to evaluate the function and the Hessian matrix at location xk. And the point of the Newton direction now is that the Newton direction, which I here denote by p and k as opposed to p, j, g, k, which was the gradient direction, this with n is the Newton direction. This Newton direction, which is of course the direction or the thing that is added to xk here, this Newton direction, namely minus the inverse of the Hessian at xk times the gradient at xk, this Newton direction minimizes this approximation of f in xk. Yeah, so the basic idea of the Newton direction is that you, as opposed to the gradient descent, is that you're not going into the direction of steepest descent based on the function f, but you approximate the function f by a simple function that you can analytically minimize, and at the kth iteration go to the minimum of this approximation of the objective function. Yeah, this step size is then just the minimum of this approximation of the function f. And I will put it here as a theorem, so of course there's a proof for that. To make this transparent, I consider the case of a univariate real-valued function, because then of course computing derivatives and so on is much more straightforward than if we would want to compute derivative with respect to vector arguments. In the end, this always looks the same. So if you look into a vector calculus where you compute derivatives of function with respect to vectors, or even with respect to matrices, the basic intuitions, like in univariate calculus, look the same, but you have a lot more notational overhead. So I wanted to avoid that. So I consider a function from the real numbers into the real numbers. And for this function, we now minimize the second order Taylor approximation. Yeah, so we have the function f, which is real numbers to real numbers, and if this the model of this function, so mk as a function of p, is the second order Taylor approximation, which I here write as you would write it for univariate real-valued function. So instead of the gradient, you have the first derivative, and instead of the Hessian, you have the second order derivative, or the second derivative, and instead of the dot product of p with itself, you just have the square. Yeah, so this is just the second order Taylor approximation as written on the previous slide for multivariate real valued functions, written for a univariate real valued function, and we now want to compute analytically the minimum of this function, and this we do like typically when we do analytical optimization. We compute the derivative, the first derivative set to 0, because we know that this is the necessary condition for a minimum, and then we solve for the location of the minimum. So if we compute the derivative of this model function mk, which is this function here, with respect to p, then of course here nothing happens, and here we have a product, so the f prime remains, so that's this thing, and here we compute the derivative with respect to p, so we get 2 times 1/2 f2 p, which is just f2 prime xk times p. Yeah, so that's then the derivative of the this model function, and then we set to 0. So we take this and say now p is our Newton direction, and we set it to 0. And there's the fourth typo. So here you would here you have to imagine equals 0 in here. Can I draw here? Maybe not. So that's equal to 0, and then if this is equal to 0, you can of course put the f prime on the other side, so you get the negative f prime, and then you divide by the f2 prime, and then you get minus, so then you get p and k equal to minus f2 prime to the power of -1, because you need to divide it to get to the other side, times f prime. And if you instead of now looking at the second derivative, again take the Hessian matrix here at xk, the Hessian matrix in this bracket, so the inverse of the Hessian matrix, and here instead of f prime take the gradient, then you are again back at the Newton direction. So this is fairly straightforward. So you just minimize this second order Taylor approximation of the function f at location xk, so with expansion point xk, and then you get the Newton direction. And this is essentially what Newton descent is about. So a minimization of the approximation of the objective function. There are issues and of course generalizations of these methods, also of the basic Newton method. So one thing is that the Hessian matrix can be quite expensive to compute or approximate. So if you think of an n-variate a function, then of course the Hessian matrix can get quite big, so it needs to there's some computational burden on this, and then it might even not be invertible depending on how it looks. So it might be a little bit hard to compute this inversion, and you actually would need to invert this on each iteration. So this is why there's a bunch of method called quasi-Newton methods that fiddle essentially with the Hessian matrix. And one way to fiddle with the Hessian matrix is to approximate it. So instead of using the real Hessian matrix that you could, for example, analytically compute, or using numerical differentiation, you might approximate it based on the gradients. And then there are many variants, and we're obviously not going into the details here. One thing that you see sometimes is this BFGS, so Broyden, Fletcher, Goldfarb, Shano form formula. So if you, for example, have looked into SciPy optimize, then one way you can use method you can use quasi-Newton methods based on this BFGS formula. And yeah, we are not discussing the details. For details, look into the books, but the basic idea is to use a Newton method, but not with the correct Hessian, but with some modified Hessian, so that it's computation more feasible. I also, in my work there on free energy minimization and variational inference, also use some Hessian modification to ensure that it's actually invertible. It gets quite arbitrary there, so you add a little bit to the Hessian diagonal, so a little bit of a value to make it invertible. Question is what that means, because you change the whole idea of this whole thing a little bit, but then yeah, you make progress towards a minimum and you're happy. In general, Newton methods can also be generalized. So like gradient descent can be generalized to line search method. Newton methods can be generalized to what is known as trust region methods. So trust region methods in general start with the choice of some initial parameter, like always, and then they are characterized by the choice of an approximation function. So in Newton methods, the approximation function is the second order Taylor approximation, but of course you can think of other approximation functions. So it's similar to gradient descent where and line search method, where in line search methods you not necessarily take the gradient as your direction, and here you not necessarily take the second order Taylor approximation. And then you minimize this approximation function mk within some domain where you think this approximation is reasonable. As you know, Taylor approximations are only reasonable fairly close to the expansion point, so they are good local approximations because locally everything is linear anyway, but they are bad global approximations. So you define kind of a radius at which you trust your approximation, and basically make sure that you choose a step direction that minimizes this approximation function, but is not going outside of a trust region radius lambda k. And if you find that if this doesn't decrease f as much as you want, you might this might be due to the fact that your approximation is bad for this far away from where you currently are, and hence you want to make your trust region smaller, so you can actually shrink your trust region at this iteration, and then actually go to 2 in this case, and choose another step direction, and then maybe at one point you find a sufficient decrease for f, and you assess the convergence. So that's the basic idea of a trust region method. Of course, it feels specifically with this determining the trust region radius, it feels a little bit similar to determining the length of the step size, but the logic is still a little bit different. So the logic is that the trust region is not how far you actually want to go into this direction. The trust region is how far you trust your approximation to be a good representation of f, and within this trust region you then go to the minimum of your approximating function, and you go exactly to the minimum and not some learning rate alpha away from your minimum. So that's then the big class of trust region methods as generalized Newton methods. And this is essentially what I wanted to say about optimization. So again, optimization is crucial because we in parameter learning, as it's called in machine learning, or parameter estimation, as it's called in statistics. We always need to minimize some objective function. We have criteria to know what a minimum is, and then there are, like I said, there are books on different methods for minimization of functions, but these methods for minimization of functions can be split into these big two groups, namely gradient methods, which proceed in the direction of steepest descent, then depending on a learning rate or step size parameter, and Newton methods, which approximate the objective function and then find the minimum of the approximation within a given trust region. Yeah, so this is these are the basic methods that are being used in machine learning, and then of course people are very imaginative, and for specific problems and for specific methods might then come up with a very specific method to minimize their objective function for a given machine learning or statistical model. Yeah. But I think with knowing about gradient methods and knowing about Newton methods, you get quite far, because every thing that you then find in a specific scenario is usually then a variant of a gradient method or a Newton method. Or it's even like in neural networks, it's straightforward gradient descent. So for example, neural networks and gradient descent is something that is very popular, and where you hear gradient descent all the time, sometimes being confused with the way that the gradient is actually computed there, which is called backpropagation. But we will get to that. Good. Again, if you are confused by the optimization routine or the optimization approach in a given statistical or machine learning method that you read about, always be aware that optimization is a field of its own, and you can treat it irrespective of machine learning. I mean, you can use optimization for other purposes, like, for example, if you want to solve reinforcement learning problems, which some people might call machine learning as well, or you want to solve Markov decision process and so on, you often need to minimize things, so you have this own field, and it's of course also feeds heavily into machine learning. In any case, there are books about it. Read the books. The nice thing about optimization, I find, is that it's relatively straightforward. I mean, the problem is very well defined. You want to minimize a function. It doesn't get much more complex, unless you talk about constraint optimization, then it gets a little bit more complex. And you basically change the parameter of this function to find the minimum. Maybe one thing then to mention is of course that you also can find the minimum or approximate the minimum by evaluating the function at all over parameter space, by doing what people call grid search or brute force approach or exhaustive search and so on. And you can do that, but if you have a large parameter space, this might take a lot of time, and then it depends on your discretization of parameter space, how exact you are. And these algorithms that we've discussed, so gradient descent and Newton descent and their generalizations, there are ways to, in a way, speed up this kind of brute force grid search approaches. Good. So that was everything I wanted to say about optimizations.